today's section, 6.1c. We're still in the section about angle measure. This will be the last part of this, where we'll talk about linear and angular speed, plus we'll start discussing our trigonometric functions. So let's begin. So first, linear and angular speed is when, if you suppose a point moves along a circle of radius r, and the ray from the center of the circle to the point transverses or theta radians in time t. So basically, if you had this point in the center, okay, and you went around that circle, you had a radius r, so the angle at which you're going around is that theta radians, and it takes some amount of t time, okay, or time t. So let's say s is equal to r theta, so that's the arc length formula that we had the other day. Let that be the distance the point travels in time t. Then the speed of the object is given by the following two formulas. Okay, so we can map it two different ways. The angular speed, meaning if you're coming from the center of the circle, how fast does it go around the middle? So we'll go around this way, like that angle change. Okay, and then linear speed is the speed that, like, on the circle, so how fast I go around out here. So those two values will be different. So that's why they're saying angular speed, just think of angles, speed, the changing of speed, and linear speed is just the speed. Like if you were on if you thought of it as a tire, and like you're starting at like your house and you're driving to school, the speed at which your tire is rotating, like, or touching the ground, so because it changes spots on the tire as you're driving, and it always rotates around. Okay, so those are the two different things that we'll talk about. So example 8 says a boy rotates a stone in a 5-foot long sling at the rate of 25 revolutions every 20 seconds. Find the angular and linear velocities of the stone. Okay, so here you have, and sorry for my pictures, but here's a boy that has a string, and he's flinging a stone at the end of it, and it's going around and around that way, right? Obviously my picture is distorted because of the space that I have, but you got the idea. Okay, now it says that the radius is 5 feet, okay, and the sling is spinning at a rate of 25 revolutions every 20 seconds. Okay, so they're kind of giving you the angular speed a little bit. 25 revolutions is, remember, a word revolution means it goes around once. That's kind of like in your car you have RPMs. That's telling you the revolutions per minute of your engine, how fast your engine is revving, or revolution, like how many revolutions it has. That's that motor spinning inside. That's what they're talking about. So we want to change that to radians, because theta needs to be in radians. So you have 25 revolutions per 20 seconds. Okay, now you could reduce that if you wanted to. So you could say that it's go down by 5, so you could also say that this is 5/4. So every 5 revolutions per 4 seconds. Okay, now if you want to change that to radians, remember you got to use your conversions, but here this conversion is a little different because you're not changing it from degrees to radians, you're changing it from revolutions to radians. So remember, once around is 1 revolution, and once around in radians is 2 pi. So I would use 2 pi over 1 revolution. Same kind of conversion, so the revolutions should cancel out, and then you multiply across. So I get 10 pi over 4 seconds. Okay, and I can reduce that. So you can say 5 pi, if you want, you can say rads over 2 seconds. Okay, so that would be the angular velocity. So, or sorry, the angular velocity or angular speed, same thing. So here, that would be that first component. Now, to get your linear speed, okay, you want to be able to use your angular speed to help you find that. So if you go back and say, let s equal r times theta, you have your theta, which is the 5 pi, right? Okay, and your 2 seconds. So then, now you need to just convert here. Okay, so here you have, let's do our linear speed. Let's say this angular speed up here, right? Okay, so now linear speed. So you want v equals s over t. You need to know what s is. So to find s, you do r times theta. Remember, your r was the length of the string, or the sling, that's holding this rock or stone, which is 5 feet. And now your s value, or the theta value that you just found, was 5 pi, right? Because it's theta over seconds. So now you multiply those, you get 25 pi. Okay? And so then now, if you use your s over your t, we already kind of reduced it, and it's down to 2 seconds. So that's our time for distance. So now v is going to equal 25 pi over 2 seconds. So the angular speed, it rotates 5 pi radians, so that's 2.5 times around the circle in 2 seconds, okay, for your angle. For your linear speed, it rotates 25 pi radians around the circle, so that is 12.5 times on the line of the circle, so this line back here, so on top of the circle, in 2 seconds. So those two things are connected to each other in the same amount of time. It's just they're talking about two different things. The angular is talking about your angular change. The linear speed is talking about the change around the circle on top, like on that line of the circle. We'll label that as W. Okay, moving on. Okay, so next part is talking about our trigonometric functions. So if we have a triangle with the angle theta, so then this side on the opposite side of the triangle, or the opposite side of your angle, is called the opposite side. The side that's closest to or connected to your angle that's not the longest side is the adjacent side. And then the longest side of your triangle is always called the hypotenuse, no matter where your angle is. Okay? So if we describe our trigonometric functions this way, we can say sine is the opposite side over the hypotenuse. Okay? Our cosine is going to be the adjacent side over the hypotenuse. Okay? And then tangent is opposite over adjacent. Okay? Now I have the other three trig functions, cosecant, secant, and tangent. Or, sorry, looks like I got mixed up there. Cotangent. That's better. So now we can do the same thing. We're going to use the abbreviations. Cosecant is the reciprocal of sine, so it would be hypotenuse over the opposite side. Secant is the reciprocal of cosine, so then you'd say hypotenuse over adjacent. And then cotangent is the reciprocal of tangent, so then you'd have adjacent over opposite. Okay? So using these trig ratios, we can write all of our trig ratios for any given triangle with a certain values for their sides. So let's say example 9 says to find the exact value of the 6 trigonometric ratios of the angle theta for the following right triangle. Okay, so here, if I want to find sine of theta, you always go from the angle that they're describing. So opposite over hypotenuse would be 2 squared of 3 over 4 squared of 3. Okay, for all of these, please reduce. So the square root of 3's go away. I can reduce this to 1/2. Okay, cosine of theta would be 6 over 4 square root of 3. So I can reduce that to 3 over 2 square root of 3. You will not need to rationalize these, so don't worry about it. If you want to, it would be 3 square root of 3 over 6. But you don't have to, like I said. And then tangent would be your opposite over your adjacent. So you get square root of 3 over 3. Okay. Cosecant will be the reciprocal of sine. So you can just take what you found for sine and flip it if you'd like. So 1 over 2 becomes 2 over 1. I'll just write 2. Secant is the reciprocal of cosine, so it's 2 over square root of 3 over 3. And then cotangent is the reciprocal of tangent, so we flip that around and get 3 over square root of 3. Okay? So that's how you would write your 6 trigonometric ratios given a triangle. Okay? Have fun.